I have the script.
Okay. Welcome back. All right, let's do this. Quick recap. Session 1, we sat here and we said, I can find it. There's 2 images here. Let's try again. Yeah, so section 1, we said from first principles, version 1 down here, as you guys remember, it says we're going to take something in that looks like the picture on the left. We're going to find its centroid, we're going to rotate it, and then if it were AutoCAD, we would hit a button that says Mass Props, and we kind of understand behind the scenes that's doing some sort of integral, and then we'll get IX and IY, right? Those are the 3 main steps. Those haven't changed. What's changed in version 2 is we said, okay, let's start thinking of this from the perspective of what the data is that we'll take in as an input. It matters now. And because we said, well, actually, the input isn't one picture, it's 2 surfaces, now we'll get 2 centroids, which automatically has an input as an impact on our previous rotate the GSC. Cannot be the second step because we haven't got the centroid yet. We have 2 centroids, right? Last session, we'd gotten up to the point where we had said, we'll take those 2 points, create a line, make a midpoint of that line, so you're down to 1 point, which we had said mathematically is not the same as, so again, if I hide the input here, green mode it up, there's our inputs, 2 surfaces, there's their 2 points, there's the line, and there's the point that's on the midpoint, and we're going to call that, for the sake of argument, we're going to call that the center point of or the centroid of the entire thing, although we know it's not quite right mathematically. So today I've basically rejigged that sketch and highlighted here in red the stuff from first principles, the stuff that's not changing. It's just we might need to worry about data now more than anything else. Okay? So last week, I think what we'll do now, because I want to stress the fact that actually a lot of times, so I can actually know that whatever comes out down here is going to go straight to here. And a lot of times when you have this type of a mentality, you can actually start working backwards from the solution this way. So we've been working starting here and going down here, right? We could just as equally start to work this way. And you may or may not have reasons to do this, but I'm going to suggest we start that way because it's the way that we had a little conversation last week where after we turned the cameras off, where are we headed with this? Whereas, we said, okay, great. I think Lily had maybe asked, does that mean now that we have this, we're ready to go? And the answer is no, because we really still have a bunch of area here before we get to the output, which is IX and IY, right? So we have to fill in that part of the script. But we talked, you happen to know that we said, because if we're sitting here and we're thinking on first principles and how we do this, right? We know that the last step is going to be something that is doing some sort of integration. When you type mass properties into AutoCAD and you press that button, he does the calculation for you. So we have a choice now. It's either we find the similar button to press in AutoCAD, or in Grasshopper rather, as AutoCAD's mass properties button, or we have to script something that is sort of like this, an integral. Now, does anybody on a daily basis in practicing engineering use derivatives and integrals anymore? Or do you just understand what they are and it's all behind the scenes? We probably aren't doing integrals on a daily basis, so we're probably not wanting to get out our integral tables and script up a bunch of integration. That's not what we're wanting to do. So we had discussed that if we were clever, what we would do is do a quick search on Grasshopper3d.com, and what we'd end up with is this component here, area moments, which would be the equivalent of whatever it's called, mass properties in AutoCAD, okay? And what does he take in? He takes in a BREP. Again, what's a BREP? It's a surface or a polysurface. It's a mesh, or it's a planar closed curve for area computation. And we get out area, centroid, we get all these different things, right? And one of them is what they're calling moments of inertia about the centroid, which is obviously something that we care about quite a bit, right? So we already know that actually something like this is the end of our script. Now I've just typed in from upstream the geometry that we plugged in. So look, he's going all the way to the back, right? So we now know that these two pieces of geometry about their own centroids, those are the moment of inertias. And just let me show you. So if you pull out a panel, if you just follow along here, you get a panel out, right? And then if I turn back on the initial geometry and I type, I think it's mass, I think it's area moments. Oop. Area moments, yeah. That's the command in Rhino. It's the same as mass properties in AutoCAD. You're going to get area moments about world coordinates, but we probably want area moments of inertia about the centroid axes. So I'm seeing here, these values right here, they should match up with these values right here. So just based on that, you guys can see that index 1, the second item in Grasshopper, is the same as the index, as what I've clicked in Rhino. Did you guys see that? It's 1.97, 8.4, 2. So we've effectively found that digitally, the parametric version of what you guys are already doing, which is huge, right? Because we said before, every time you do this, it's the same process. It's do this, then this, then this. And this was the third final thing. So we've already, we've already digitized some of our workflow just by being a bit clever. Now, what was the main problem that we said last week? What was the main trick? Now, we said last week, here's the deal. We're trying to automate this workflow. And when we automate something, we have to take on certain responsibilities that when we click mass properties in AutoCAD, he's doing a lot of things behind the scenes that we take for granted. This guy right now, he's basically giving us two moment of inertias. And the moment of inertias that he's giving us are the moment of inertias, as we said before. Let's say on my sketch here, we've got a centroid here, and we've got a centroid, I'm just going to draw it up here so it's a little bit more obvious, right? So if we got IX, for instance, that would be IX, and that would be IX, assuming that this is the global coordinate system, where that's Y and that's X. And we sat here and we said, is that really what we want? Do we really want two moment of inertias? No, right? We said that globally we've gone through all this pain right now to determine that that's the centroid of both shapes. And we want the moment of inertia about this point right here, right? So we're in a pickle because we have a tool which will give us two pieces of information that relate to the answer in some way, shape, or form. But he doesn't actually do exactly what we want him to do, right? He also didn't actually give us exactly what we wanted for the find centroid, right? So we had to, this isn't new to us. We had before a situation where we had to basically, actually I drew this over here, but if it's honest with what we've done before, is what we did before is we drew this, and then we got this one right here, right? So in the same way that we had to come up with something like this to massage the data into a format that helped us, in other words, to go from two centroids to one centroid, we're saying we're going to skip this part right now because we're going backwards. But we realize, hey, we're going to use this component. Now here's the question. What can we do to go from this guy right here and this guy right here to these guys, which are about this centroid right here? Anybody have any ideas? We talked about it last week. Use that mathematical equation you taught us about last week. Yes, and that equation, so I'm going to move this guy up, or just move these guys out of the way, because we know what's going to happen here today. We're going to formulate on paper first one of the translations. So we're already sort of in global coordinate systems, so let's leave that out for now. And we're going to focus in today on, let's assume we today want to walk out of here with the moment of inertia about that centroid, the global centroid. So I'm going to draw it in a different color. We want the moment of inertia about that guy. That's IXX and IYY. just to be clear. Those are the final things. So that's I, X, X, I, Y, Y. And we're saying here, hey, listen, forget about rotate for now. We'll get to that later. If I now have, at this stage of the game, if I have an ability to get IX1 and IX2, I also have, again, going back to the colors here, I also have this centroid, right? Where'd that guy come from? He came from here, right? He came from here. We already know we can take these two guys and get this and get this. So those guys can come right down here. So how do I go from those guys, again, input, to the output, which is effectively these guys right here? The mathematical formula we talked about, and again, this is really where we had said, you normally wouldn't, do you guys remember, I mean, you guys probably didn't learn it in English, but like parallel axis theorem. Like, that's a theorem, like, that is probably something you learned, right? And that's where it kind of comes down to, you might, I think last week you guys kind of laughed, you goes, oh my God, we're talking about parallel axis theorem. This is stuff that I forgot of way back when, right? And we talked, if we want to get more benefit than, let's say, AutoCAD allows us, AutoCAD's not in the business of helping us out any more than they already have. They haven't changed since the 90s, and they won't change since the 90s. So if we want to actually get something that gets us streamlined work, we have to take a little bit of responsibility of what AutoCAD mathematically must be doing behind the scenes. We agreed last week. He must be, if we give him two surfaces, and he's doing something behind the scenes, he must be translating stuff around for us, because he gives us one value rather than two. So now, it's our responsibility to sit here and say, okay, well, that's just math, right? So for us to actually, you know, we learned it, and it's not that hard, and maybe you need someone who is a nerd like me to say, oh, no, not nerd, parallel axis theorem, and we're pretty sure we could remember that, right? So let's bring it up. Wikipedia, free knowledge here. Oh, integrals. Okay, for those of you who can't remember it so well, I think last week I nailed it. I think last week this was the one that we said, yeah, there you go. So they said the moment of inertia as described about another axis, right, is equal to the moment of inertia about its centroid times its area, or mass, depending on what you're doing, times the distance squared. Those are all things that we have, right? So in the grand scheme of things, if I just write that down, right? So I'm going to erase the name here. And this is, I'm doing it in this way because I want to show you guys that this isn't just about geometry, this stuff. It's really, you can use everything that you're doing in Excel, you can do in Grasshopper. So what did it say? It said, I'm going to do colors again. IXX, for instance, it equals area times radius squared plus IXX. Again, IXX being about its centroid, area being the area, and radius means the distance between these two guys. R1, R2. Sorry?
X1. IX1.
IX1. Yes, sorry, you're catching me on. Good call. Thank you for that. Thank you. All right, so there you go. Blue stuff is the stuff that we have. Does anybody disagree that we don't have these three variables?
I think I agree, because typically, because two frames, they're not one component. They're just assembled. But some contractors, they run the mesh property on AutoCAD as a one piece.
Yeah.
Which gives better I values. But actually, they're not one piece. They just assembled together.
Do they act structurally together so that the shear flow can sort of make it act together? Is it welded? Or
they're not welded.
They're not welded together.
They're not welded together.
Right.
So if they run mesh property on AutoCAD, it shows up really great I values.
Right.
So some people, they add, let's take only 70%. Some people said no, 100%. There's some argument. There's no clear standard to how to calculate that assembled frame.
That's interesting. So basically, right now, this frame. I mean, as a structural engineer, I'd look at this and I'd say, if at these connection points, what look like connection points, it's a rigid. If the shear flow could interact. Can shear flow happen between these two shapes? If it's bending? Not really.
Not really. They're just assembled like this.
Interesting. Okay. So there is no real rigid. They're not welded.
There's no welded. There's no screws in between.
This is big. All right. So this is me projecting some sort of an idea. Again, you guys get what I mean. If we have rigid connections between these two, then the contractor might be right. What you're saying is actually it's not so straightforward.
They're supposed to move.
Yeah, because they can move relative to each other, which makes it a bit more of a different problem. So in other words, maybe it's not clever of us to start playing with parallel axis theorem and bringing them together, because it's actually not relevant to the engineering behind it. So in that situation then, so if we went back to the drawing board and we said, well, actually, that would be nice if it was welded, but we don't have something that's welded, which means they both kind of act almost in parallel from the bending, right?
But I think that's why we can use that algorithm.
The parallel axis theorem. For now, I guess it's the easiest way for in the purposes of teaching Grasshopper. This is probably the easiest way for us to go forward. However, I think it's a really good point because, again, if our first principles are off and it's not welded together and it doesn't have shear flow, then all of this is for naught.
I mean, if you calculate based on this algorithm, then probably less value than you do on AutoCAD.
I would hope it matches perfectly, actually, because
really?
it should be almost the same. Let's see. Let's test. It's an experiment right now.
Well, that is how you choose in your AutoCAD. If you choose like two sections together, then they give you it should be exactly the same value as this one. But
Then
if you like do it
separately and then just plus,
then I guess it's different.
If you did it separately in plus, I think that's
Definitely different.
Well, that would be, hey, listen, we better be bending two different sections on their own, basically, about their own centroids, which is a bit funky.
and also some people they run best property separately.
Yeah.
They just plus together.
Yeah, they say so each one bends about its own centroid, and then we just add this capacity.
Also, that's not correct.
Yeah, I was going to say, like, all of this sounds like it's a bit sketchy. But anyways, for the purposes of this conversation, let's pretend they're welded together. There can be shear flow, or there's bolts or something like that that can handle the shear flow, and it acts as one section. In that case, no one here is going to have any objections to saying these variables, A, R, and I1XX, we own, right? Because we already played with them. We have them on the canvas. There's IXX1 and 2. We said we have the area here, right? All the way back up here. And we have a line here, which obviously we could start, getting out the distance. It's, we said it's at the midpoint, the centroid, so it's obviously half the length of that line, right? So this is the lesson in basically, as long as we get this first principles down, and assuming it's right, then it's going to be very easy for us because our answer is a function, a mathematical simple function of everything we already have, right? And then it would be, exactly as Bianchi said, if you're adding it this way, where you're saying IXX2 plus A2 R2 squared, and you get IXX as well out here, then you can sum these two, right? Because they're both mathematically linked by the parallel axis theorem. But I don't think you can just go in there and start adding them together. That doesn't make sense, right? That's why they have this theorem, right? So that's our plan. It's as simple as that today. It's take that algorithm, A times R squared plus IXX1 or 2, and get out two moment of inertias about the centroid, and then sum them. Okay? That's the first principles plan. What is the thing that we talked about ad nauseum last week in terms of what's our... So we have our plan. What do we do with our plan then? What's the first thing we do? Okay, so what's the first thing we want to do, let's say? Let's start here.
Gather the distance
Gather the what?
of the line. What's the distance of the...
Yeah, so let's start to collect, let's say. Let's, in our script, collect all the variables first. So if I'm you guys, I'm sitting here right now and I'm saying, okay, I have 3 variables I need. I'm going to go shopping. Data, copy, paste, paste. I'm going to right click there and I'm going to say R, that's one of the things we need. IXX with a small I, and A, right? And just for the purposes of staying clean here, what's going to come out the back? I'm going to put I capital X, okay? Does that make sense? So those are data buckets, guys. Just to remember, data, if you right click on one of them, they do nothing. They just help you kind of think straight in Grasshopper and keep things nice and clean. So that if Byongi wants to come and check your calculations, like it's not looking like a mess in your canvas.
Data means?
Data just means a bucket that holds data. It doesn't do anything, any data.
Can be
Any
numbers.
data. Yeah, numbers, text, booleans, geometry, BHOM objects. So everybody try and mimic this right now. Go ahead.
对的。
Remember those buckets of information. Again, when they look like this, they're buckets, I call them, because they don't do anything. They always will have these little hexagon emojis that you guys see right here. So if I just do data, I know which one I want because it has the little hexagon emoji right there. So once you guys have that up, then it becomes an issue of, again, this is just, we're just repeating what we did on the sketchpad over here in Grasshopper, right? We're not doing anything new. So now let's go shopping, right? Let's go shopping for data. So first things first, I'm going to move this guy over here, the area moments guy, the guy who's basically calculating IXX, right? So that's why he would go in there. Sorry, Jane, 1 second. I'm just going to see you looking at the screen.
Area.
So yeah, we're going to, there you go. Look at that, Byongi's already realized. Actually, this guy right here, area, and this guy right here, area, same thing, same, right? So it's just very convenient to shop for that information right here. And then the R, what did we just say? The R, based on our previous definition, for both of these guys is going to be the distance of this line right here divided by 2. So I want everybody to try it, shop for yourself. Put R in there yourself. I'm not going to tell you how to do it. Let's see how you guys get it. Delete what? Oh, the wire? Oh, good question, Wan Ling. Guys, another mechanical skill for you that Wan Ling has here. So she wants to, let's say, for instance, remove, she's calling it a link, these wires, right? These wires, if you want to disconnect something from something else, right click and say disconnect. It gives you a little preview that says, you know, what you're disconnecting, and then it disconnects. So connect, and then right click, disconnect. And if you so chose, let's say for instance I want to put the area in here, but I also want to put in whatever this G is, you press shift, you see how the little button down there changes? And then shift, and then it can go in. So see how it has a plus when I press shift?
Very little one.
Right? And if you want to take it out, actually there's another way. You press control, and you do that. I never do that,
Oh,
but
that's better.
yeah, in many ways it's skin a cat. Who's on the R? Who has an R to share with the group? Lily? What's your R?
25.
25. How did you do it?
Is that right? First one.
Oh yeah. Right. Do you want to, maybe can you do it on my screen so that the people at home can see? Okay, fine, I'll just memorize it and then do it. Okay, so Lily has gone out there and she has found this component that says evaluate curve. I think we talked about it last time, but you guys know how to find components. She said 0.5. She's gotten that midpoint of that line, and then she's done a distance, effectively, between that midpoint, which, by the way, we've also... Oh, that's where she's gotten it. That's what we had last time. The distance between this guy and, I believe, that guy, right? So, what is this guy? If I just put out data, just so I can grab him on his own. That's that guy, right? And then what's this guy? 2, right? And then it done distance, that's the 25 millimeters, whatever it is, to the R. Okay, so cleverly she said, listen, the first thing you did, right, was double click distance, and then realized I just got to cherry pick off my canvas here 2 points which matter to me. If it were me, here's another little trick for you guys. I would have said length, and I would have, you know, there's a lot of different lengths, but I would have looked here and it says measure the length of a curve. I would have got this guy, and then here's one for you guys. I would have right clicked here, expression, and expression just lets you put in a mathematical equation. So x over 2 is what I'd put in there. And then what it gives me is the same result as you, and it's a lot more, you know, there's less components, so it's a little bit less messy. Whatever you want to do. The key is you're doing math, effectively, on geometry. And this is the important part, is everything that you are doing anyways is involving geometry and math. That is a huge part of our jobs, especially for facade engineers, right? Geometry linked with math. A lot of times the math influences the geometry, and a lot of times the geometry influences the math. The key about this place and what we're doing today is usually, if you want to do math, you're either doing it on the calculation pad or you're doing it on in Excel. What I'm here today to try and tell you guys is all we're doing today is math, but we're not using Excel. We'll be using Grasshopper, which is great because Grasshopper is a great medium for not only math, but also geometry, whereas Excel is only a good one for math. It's not to say that you shouldn't be using Excel. It's just if you want something that's extremely helpful to you, sometimes you need a better tool. So does everybody have inputs to this function? One link? Not yet. Come over. Looks like Bianchi's done shopping. You're done shopping too. You have 25? Just hover. Yes, you do. You were hovering over the equation here. All right, so guys, just FYI, when you do this equation business, Wan Ling was hovering here, and she goes, I don't want x over 2, right? But it's because you're hovering over the little symbol that means equation. So just move over here, and she's got 25 here. So 25 here, and the expression that you've typed in there. So you have to just right-click the L. And then express, yeah. Guys, when you're right-clicking these things, you have to be kind of very precise. Sometimes you were right-clicking, but not exactly on the L. Right? So just for the people at home, if you right-click here, you're not going to get what you want. Like you have to kind of be right on top of the L, and then expression editor. Okay, and Lily's already got it. All right. So next big thing is we know what's going out here. If I do a scribble, I already know this is IXX plus A times R raised to 2. So you might be saying, okay, that's math, right? So now the question is how do I do math in Grasshopper? Huh? Math, yeah. So there's a few things here. What was the first thing we should do always when we want to check out if something's available to us? What's one of the things that we want to do right now? We want to probably multiply something or get the exponent of something, right? So let's just see. Let's say we want to get R squared. Exponent. Nothing comes up. Squared. Oh, hey, what's that? Compute the square value of a value. The square of a value. Sounds perfect. R squared is 624, right? Almost 625 because it's 25 squared. Simple as that, right?
Can you do that like this?
So yeah, you saw what I was doing. So you could do it all sort of behind the scenes as well. So you could, the data buckets you can't do math on, right? So you could use a data bucket here, or you could use a number bucket. And the number bucket is the same thing, right? It's just a bucket. But if you right-click it, you can put an expression in there. But I would advise against that because of one main reason here. Because it's a little bit hidden at that point. Because this is a very easy thing for you to read. R squared, right? The next thing we might want to do is, what? Multiply, right? So you might say multiply.
So basically you use all the equation from the
Yes.
icon.
And then between this and just looking at this, it's very easy for someone to come in and understand what's going on. If you hide it all behind the scenes here, not that this is wrong, it's just, I think, harder to understand. So you can do whatever you want. It's just the issue of the data buckets themselves won't have that functionality. So let's see who can get to the IXX first. The capital IXX. So there's your equation. There's your data, your inputs. See if you can find all of the math that you need. Let us see. Okay, let me try and, because I have to replicate it for people. Okay. I know that. Okay, so FYI for anybody who may be interested more, like Bianchi, in these expressions, here's what Jane has done. And this is a quintessential example of when you get an error, you click on this button and it says, expression generated an error. Good. Invalid expression. Expected parentheses instead of slash. Effectively, this one's kind of hard because what you need to know is when you use these things, x is the variable, not length. So you have to choose x, not that, and then it will work.
Always X.
Always x. Okay, so the next thing you guys should have found already is well, I got this part of the equation done. R squared times A, that's this part. So the next thing I need to do is addition. Right? Addition is the main guy now who's left. Oh no! What's going on here? Vectors cannot be added to numbers. Everybody see if you can get to there. I think we talked about this before, but I'll mention it again. A computational engineer, it's very used to seeing red and orange on the screen. It will always happen. The new skill that you're learning is how to solve that problem. Engineers are good problem solvers, so don't be, when you see this, go, oh my God, this tool's crappy and it'll never work. It will work, you just have to understand what's going on here. Vectors cannot be added to numbers.
So the distance do a vector.
You're saying, let's do something here. Vectors, so it's telling us we're trying to add a vector to a number, right? Which is obviously not right. So let's look. If I hover over A, those are two numbers, right? So obviously, IXX must be a vector. And if you just look at the text, you know, what they're showing you here, yes, those are not numbers. Like they're numbers, but there's also commas, there's other stuff, right? And if we go all the way back here, what does it show us? The little emoji says it's a little arrow, it's a vector, right? It's not a number, right? And you guys remember this, like it literally is that a moment of inertia. You know, when we do moment of inertia, we use our right-hand rule type of thing, right? So it is a vector. That's why you have to use the right-hand rule. So this comes back to one of the main things, I'll pull it up right now, of chapter 1, again, chapter 1 being important, where we learn a few key vocabulary terms about Grasshopper. And one of the key terms that Grasshopper is if you want to get information which is inside something. So for instance, if you want to get the coordinates, the XYZ coordinates of a point. So a point contains 3 numbers, right? If you want to get the 3 numbers that are down the hierarchy, the word is deconstruct. Okay? So that's just a new term for you guys to remember, like BREP. If you want to get what's inside something, the key cheat code is deconstruct. If you want to create something, so if you want to create a point from 3 numbers, it would be construct, right? That's a big thing, because you will spin, look there, I even have the Google Translate for it. Create something, construct. Take something apart, deconstruct. So what we know right now is if we just look at this shape has a moment of inertia about its centroid in the X, Y, and Z directions, right? So let's deconstruct this vector. Deconstruct, look at all the things that come up, right? Lots of things that you can take apart. And then we say vector. And look, the emoji basically gives it away. Look at that emoji. Again, this tool was made for architects, so it's a lot of emojis, a lot of very pretty stuff going on. It's very easy for engineers to pick it up. And what do we get out? 3 numbers, or 2 numbers rather, but 3 outputs. Now let's stick with IXX. Let's say that we're doing IXX, which means we'd want to grab the X, and yay, no more red, which obviously means good, right?
Can I just use deconstruct rather than deconstruct vector?
There is no deconstruct. Like you deconstruct that one. So that one is, again, you guys remember last time we talked about languages and how it's kind of inconsistent. This says deconstruct and you think, oh, it can deconstruct anything. But actually this one's deconstructing a point. Now it might work. 2.4913. 2.4913. So somewhere he's doing a calculation. Because this guy, look what he says. I want a point. See the emoji?
Input point.
And then this one wants a vector. So a lot of times, that's why it's really important that you kind of know exactly what's going on, because he tries to be smart for you. Because a point is not a vector, right? It's just physically not the same thing. But apparently behind the scenes, what he's done is he said, listen, if this guy, if you give me a vector, what I'm going to do is I'm going to treat the vectors XYZ as a point XYZ and just give you that back. In this case, it would work. In other cases, it would not work. Does everybody get that, what we're talking about there? Really? So look at this. Byongi said, Medio, you said deconstruct is the magic word. So I'm going to type deconstruct, and the first thing that comes up is something that says deconstruct. Beautiful. So that might be the generic take anything apart type of thing, right? If you read it, which you might not, because you might say deconstruct is the magic word, so I'm going to click it right away. If you read it, it says deconstruct a point into its component parts. which is actually kind of confusing in and of itself, because all it's doing is give me the coordinates of a point. That's what it should say. So we click that, and he says, remember, when we hover over an input point, it says here, we hover over the input letter, it says what he wants and what type of thing he wants. In this case, he wants a point. His life is, you give him a point, and he gives you back 3 numbers. So theoretically, if you give him a B-rep, or you give him a number, he should not be very happy, right? We can even test that. So if I just give him a number, he's going to go, data conversion failed from number to point, right? And we understand that because a number is not a point, and he's asking for a point. Equally, Bianchi says, well, if I give him, he's noticed, if I give him a vector, he still seems to work. So what's going on here? And all we're saying right now is, we're going low energy here, all we're saying here is he's doing something for us. He must be, because he still gets the same answer, right? 2.49, 1.97, if you see it there. And this one, which is for a vector, deconstruct vector, is giving the same answer. So it really comes down to, this issue comes down to solely, do you understand, when you use one of these components, not only what type of data does it want? The type of data is extremely important, because as far as these components go, they live to take in one type of data and give you another type. But sometimes they'll try and get clever and convert a point to a vector or a vector to a point, which may not be what you want it to do.
Because I wasn't aware of that this I and IXS was a vector.
Yes.
But I wasn't aware that they are just transporting data.
Yes.
And then we realized he's wanting that this is the vector, it's
Yes.
not the numbers.
So this guy was the one to alert us. And here's the thing, he brings up a good point. This guy right here, he worked. So he took a vector, he wants a point, but he will take a vector. Whereas these guys, they want numbers, and they won't take a vector.
So, because I was using this one, and I put X to A, B, and still it worked. So,
Yes.
if I use that one at the first time, I wasn't aware of that they're carrying out all the vectors number.
Yes.
Vector.
But that's a really good thing to bring up, because look, this guy, a number won't take a vector. He's not doing anything to help you. But this guy, he's supposed to take a point, but he'll take a vector. So again, it's really, really important. That's what chapter 1's all about, is do you understand what type of data you're meant to be giving something? In other words, for math, don't give me a circle here. Don't give me a vector. Give me a number. And in this case, I would say you go deconstruct vector, you give it the x value, and boom, there's 2 values. But we still have one more step. Going back to our original conversation here, we said that there's one final thing. That gives us 2 ix values. 2 ix values, but we need to do a summation. And this one's another interesting one. Let's see who can figure out how to sum 2 numbers. So what have we ended up with? We've ended up with a list, of 2 ix's. And we're saying now that because of the mathematics, we can sum those 2, and it will give us the number that we want. So, again, what do? Double click, and we say sum. I don't see anything there, right? Addition. Well, this is the one we just used, right? Perform a mass addition of a list of items. Again, this is not mathematical. This is an architectural program. So they've made this up. I've never heard someone say in engineering, I'm going to do a mass addition of numbers. That sounds like something from physics, right? What this guy's saying is, please give me a bunch of either numbers or vectors. Look here, Bianchi. He said, you see the emoji, guys? Input doesn't have one of these. So the people at home see what I'm showing here.
Yeah, also, it's come up with mass addition and mass multiplication.
Yes. So what he's saying here is input values of mass addition, either numbers or vectors. So he takes in a list, and what he spits out is one value. So he takes in a list, and he'll spit out one value. And this is another one of those things is, we wouldn't call it mass addition. We would call it summation. But because you were proactive and you said, let's not try summation, let's try addition, we found it. And guess what, guys? That, in theory, if I pull that out, okay, that in theory is the same math, the same exact thing, if we did what we did in AutoCAD normally. So if I take this, I do mass properties, area moments, I think.
Mass property. Yeah.
No, mass properties in AutoCAD, area moments in here. About his centroid, drum roll please, area moments about the centroid, IXX is 4.48. 4.48 e to the 6. So we are off by a bit here. We're in the ballpark, but then again, we did say that we're not doing the math extremely correctly, let's say, to get the centroid of these two objects, right? So let's see here. Let's just make sure about this centroid. Okay, so we're off by a decent amount here, 20%-ish. But it's not, it's a good starting point, right? Because now we've learned a lot. So let's just take a look. If I look at the centroid, if I say centroid here, area centroid. Okay, boom. That's the actual centroid. We'll just put a little circle there. That's the actual centroid, and this is the centroid that we've assumed. Right, so those are off. Ah, I know what we did wrong. Does anybody know what we did wrong? The answer's on the screen. This is part of the problem. I was running out of space here. Obviously this got pretty messy. Let me save this. Let's just get a new canvas here. We broke the rules of parallel axis theorem. What did we do wrong? What did we break? What rule did we break? We called that R, right? You got it, Lily? What did we do wrong? We took a value that does like this.
Yeah.
So we broke. No, here's the thing. The good news for us is actually what that line is almost orthogonal to IY, right? So we almost have this picture about Y. But let's look here. So we said this is not correct, but it's almost the same as what should be IY. So if I take Y instead of X, 1.5 e to the 6th. Let's see if that works. Area moments. Now that's a lot closer, right? But we broke the rules because we weren't paying attention to the physics of it, right? Or at least the geometry of it. But we're very close now. I think we would almost say, hey, that one's good enough for us to keep going. But we're going to fix it, right? But at least it's within a few percent. And we know exactly why it's not working. So, what's the problem here? Is the problem anything in here? Not really, right? The math is still going to be the same. It's the input before here, namely this guy right here that we have to play with, right? Okay.
We have to measure the distance error to center.
It's got to be, so we'll have two of these components. One of them will be using Y, and one of them will be using X. But we need to get the X component of this line and the Y component of that line. So in other words, we've gotten the y the x component, which goes to calculate IY. We now need to try and figure out, how do I convert this guy right here? We do some trigonometry type of stuff, right? So we basically, I've drawn that very poorly. We want this y, and we want this x. And we're saying, luckily for us, this x, which goes on to calculate IYY, is the guy. He's almost right, because the cosine is, the angle is very low. But that's why the other one that we saw was way off. So we can pick that up in the next lesson. But you can already see, there you go. We made a lot of progress today, and after next lesson, we'll basically have a calculator for a moment of inertia, assuming that it's two surfaces on the input, which obviously you might not have, but then we can also start to work and say, how can we make it more generic?
But my MA seems doesn't work.
Okay, let's see if we can solve that before we adjourn.
Because it's,
Oh, so somehow, I'll show everybody. So somehow Jane, her MA looks like this, right? And what I'm doing here to do that is I press my middle mouse wheel, so I push that down, I get this menu, and then there's the on and off buttons here. So you've accidentally turned that off. Now sometimes that can be very useful, but you know, be careful not to do it on accident. The other thing is to just kind of remind you guys, if it's geometry, so let's say this point, right? And I turn off green mode. So look at all the stuff that's on my screen right now. Everything is being shown. What if I just wanted to see only the final product, which is the centroid, right? If I grab everything, now look at the colors, middle mouse wheel, blindfold, see how they're a bit darker now? And did you see how basically, if I undo that, you see how on the left side, it's going on and off, right? So that's a big thing. We've been working in green mode where you don't see anything unless you click it, but this guy right here, when you click middle mouse wheel, is very useful because you can make the groups, you can turn stuff's visualization on and off, you can turn stuff literally on and off, you can bake things. So for instance, if I want to put that green point out into Rhino, I click bake, and now he's there. Or, let's say I'm all the way out here in Timbuktu. That happens sometimes on a project. And you're like, where is this point in Rhino? If I do the middle mouse wheel and I click this guy, he zooms right over. And that's extremely useful on a real project, right? Because you want to, you'll start to develop a skill where you're like, I know what this is, but I don't know where it is in 3D space. So you just go boom, boom. Extremely useful menu here. So today we covered effectively a couple big things just to review. One, showing you guys that mathematics that you would normally do in Excel can definitely be done in Grasshopper. We talked a bit about construct and deconstruct, which are sort of big concepts for you. And I highly recommend that you do your smiley faces because that's what we cover in the smiley faces. And then we discussed a bit more about some of these little Grasshopper specific items. So I would recommend that before next class, again, we should all be trying to be here for next class, if you're not there already. But when I say being here, is doing it without me in the room. So hopefully that will only take you 15 minutes before the next class to sort of get straight up back to where we are right now. And then next class we'll finish off this mathematics here. And then we'll move on to making it a bit more flexible. Because right now, obviously, some of you are probably saying, well, sometimes it's not just two surfaces. Sometimes maybe it's two polylines. Or maybe it's 3 polylines. So how do we make it generic? Any questions before we adjourn?